Have you ever wondered where thousands of liters of cooling tower water disappear every day? Or why does a cooling tower continuously demand makeup water? And why do power plant closely monitor a parameter called COC? If these parameters are not properly controlled, your plant can face scaling, corrosion, biological growth, poor cooling tower performance, and even increased turbine heat rate. In this video, I'll explain what is evaporation loss, drift loss, blowdown loss, COC, and makeup water requirement with simple formulas, practical calculations, and real power plant examples. Hello friends, welcome to my YouTube channel Power Plant Practical Knowledge. In this video, we will learn water loss due to evaporation, due to drift and blowdown losses and the chemical parameter cycles of concentration, nothing but COC. Evaporation loss is the loss of water that occurs where the water gets converted into vapor while removing heat from the circulating water. This is the primary cooling mechanism of a cooling tower. Evaporation loss can be calculated by using a simple formula 0.00085 into circulating water flow into range. For example, here if you consider circulating water flow as 5000 meter cube per hour and range 10 degree, nothing but difference in inlet to outlet water temperature. If you substitute all these values, you'll get 42.5 meter cube per hour. It means circulating water flow at 5000 meter cube per hour. Evaporation loss is 42.5 meter cube per hour. Plant must compensate this through makeup water. This evaporation loss is unavoidable and is the major water loss in a cooling tower. What are the factors affecting evaporation losses? These are high circulating water flow, high range, high heat load, and summer operation. These are the reasons which increases evaporation losses. Another loss is drift loss. Drift loss is the water carried away by air in the form of tiny droplets. Unlike evaporation, here the water is not vaporized. Actual water droplets escape from the tower. This drift loss leads to water wastage, salt deposition, equipment corrosion, and environmental issues. Drift loss can be calculated by using the formula circulating water flow into drift percentage. Usually this drift percentage range from 0.001% to 0.005%. Here we'll take an example where circulating water flow will be 5000 meter cube per hour and the drift loss is equal to 0.002%. By substituting in the formula, you are getting a drift loss of 0.1 meter cube per hour. Nowadays, modern drift eliminators keep drift loss very low. If the drift loss is more than 0.02%, then the cooling tower performance is very poor. Keeping drift loss in the good range saves water, reduces environmental impact, and lowers operating costs. What are the problems we face due to high drift? One is water wastage. Increased drift leads to significant water loss, increasing makeup water requirement. Another is the salt deposition. Drift droplets carry salts that settle on the surrounding surfaces, causing deposits and scaling. Another problem is nearby equipment corrosion. As droplets escape, these salt-laden moisture accelerates corrosion of nearby equipments and structures. Another problem is environmental issues. Drift can affect air quality, soil, vegetation, and nearby water bodies. Another loss is the blowdown loss. What is this blowdown loss? See, when water evaporates, only pure water leaves. Dissolved solids remain in the circulating water itself. Their concentration with respect to time keeps on increasing. To control this concentration, some water is intentionally drained. This is called blowdown, and the loss occurs is called as blowdown loss. This blowdown removes concentrated dissolved solids from the system, protects equipment, and maintains water quality. Blowdown loss can be calculated using formula evaporation loss divided by COC minus 1. As we already know, evaporation loss is equal to 42.5 meter cube per hour and COC 5. In the coming video, we will learn about COC in detail. Now, substituting the values, we are getting blowdown loss as 10.6 meter cube per hour. It means 10.6 meter cube per hour water must be discharged continuously to control TDS. What happens if this blowdown is low? If this blowdown is low, it causes scaling, fills choking, condenser tubes fouling, and it reduces heat transfer in the condenser. Another way, what happens if the blowdown is high? It causes excess water wastage, high chemical consumption, and increased operating cost. So, blowdown must be tuned and blowdown loss to be controlled. Next, we will learn about chemical parameter COC. What is COC? COC indicates how many times dissolved solids have concentrated in circulating water compared to makeup water. COC can be represented as TDS of circulating water divided by TDS of makeup water. COC can be calculated using circulating water TDS divided by makeup water TDS. Here, circulating water TDS is 1500 ppm and makeup water TDS is 300 ppm. Substituting these values, we get COC as 5. COC 5 means cooling tower water is 5 times more concentrated than makeup water. Typical COC values are if COC is in between 2 to 3, it means poor operation. If it is in between 4 to 6, normal operation. If it is in between 6 to 8, excellent water treatment. What are the benefits of higher COC? Lower makeup water requirement. Higher COC reduces the need for fresh makeup water. Another, lower blowdown loss. Higher COC means less water is lost as blowdown, and better water conservation. Higher COC helps conserve water and protect resources. Even very high COC is also a risk as it causes scaling, mineral deposit form on surfaces and reduce system efficiency. Another is a corrosion. High dissolved solids and chlorides accelerate metal corrosion. Another is a fill blockage. Scale and deposits clog the fill and reduce water distribution and airflow. Another cause heat transfer reduction. Scaling and fouling reduce heat transfer and increase energy use. High COC saves water, but excess COC can damage your cooling system. Till now, we discussed about various losses and calculated the losses. The summation of all these losses, nothing but the makeup water we need to put in the system for circulating. As we calculated the operation loss as 42.5 meter cube per hour, drift loss 0.1 meter cube per hour, and blowdown loss 10.6 meter cube per hour. Sum of all these losses is 53.2 meter cube per hour. This much of water we have to make up every hour to run the system healthy. 53.2 meter cube per hour means per day it will come around 1200 to 1300 meter cube per day. Therefore, maintaining proper COC, drift eliminators, water chemistry, and blowdown is critical for plant economics and operating cost. A cooling tower not only cools water, it also manages water quality. Therefore, to maintain efficient operation, control evaporation loss, minimize drift loss, optimize blowdown, and maintain proper COC. These four parameters are the foundation of cooling tower water management and plant efficiency. If you found this video useful, please like, share, and subscribe. Thank you.